Hello, friends. This is a quick video for the Foundations of Mathematical Proof class, Math 231. I wanted to run through some things with the syllabus, as well as maybe talk about a little bit of getting into the whole thing of the class. I have the unfortunate situation that I have a doctor's appointment on the first day of class. So that means I'm going to be a little bit late. And so hopefully having had this video will have, kind of made up for the cut into our time together. Okay. So let me talk to you about the syllabus real quick here, assuming I can remember how to do that. So there we go. All right. So this is the syllabus for the course. There should be a link to it from the homepage of the Canvas class. And I'm going to try not to read this to you, but it's hard for me to not read things that are sitting on the screen. So the basics of it are just giving you the information that you already know or that you might need that you haven't thought of. Course name and number, the semester that we're having it, and then the contact info for the teacher. So all of y'all know me already, and I think that y'all have been to my office before, but just in case you haven't, it's over here in Frank Family Science 234A. And then I'm giving you my cell phone number rather than my office phone number because my office phone doesn't work. So there's my email as well. And you can find that. If you can't remember that, you can just type in Marlin on Gmail from your campus account, and it'll autocomplete for you. So course meetings are going to be Tuesdays and Thursdays, 10:45 to 12:45. Once we don't have conflicts with that. My office hours, I've got them on Monday, Wednesday, Friday at 10 o'clock. And then I put one in the afternoon on Thursday. Okay. And prerequisites for the course, everybody has this. Things that this meets, it's required for a math major from a certain direction. Excuse me. From a certain direction, it's required of a math major, but for a different direction, you can use it to satisfy requirements as well. So here about the actual course description for you. This is more than anything meant for somebody who receives transfer credit for this course to see what the course was supposed to be about. Okay. There are at different schools lots of different names for basically the same course. Other math teachers refer to this as the bridge course because it bridges the gap between the calculation-oriented math that people are used to thinking of and the logic-based math that comes along later. And so the big thing that we're looking to get out of it is formal reasoning stuff. It's a 4-credit course, and I have to put in here how many hours per week that I think that you'll spend on it. Not sure that you'll really be spending 12 hours a week outside of class on it, but hypothetically, that could be the case. Okay. And required materials for the textbook, required materials for the class are, there's not an actual textbook. I will instead give you a PDF of problems that you'll be working on, and the resources that you have for that. I'm not going to expect you to be doing things where you're doing readings. Instead, what you're going to be doing all the time is just struggling with the logical concepts and how to convince me that something is true when it probably is really obvious it is, but the reason it's true is sometimes hard. So you do need to have regular access to a computer. I don't mean a phone, a computer. You need to be able to type math, and math is notoriously hard to type. And just don't try to rely on your phone for that. Okay. Course outcomes. Again, these are something that somebody with transfer credit or looking at accreditation or something might need to know more so than y'all. But it gives you kind of a basic rundown of the kind of things that we'll do in the semester. Then this bit about the ADA accommodations. If you have some sort of learning difference that you need some sort of adjustment for, talk to me about it. It is likely the case that we can facilitate something like that super easy. Okay. I understand with regard to such things that often people feel a little bit embarrassed and don't want to like talk about them in front of other people. But because of the nature of this class, if you got, some bit of difference about stuff that we need to accommodate, probably we're all going to just work together to figure out what to do. It's kind of the nature of this sort of class. The honor code is a big deal here. And so I need to talk about this, not just read this to you, but talk to you about it. What you will get out of this class is practice at reasoning and arguing. I like to say you get practice at being right. Okay. You convince people of something, not in the sense that, a court of law, somebody might browbeat somebody with an idea and just state it forcefully and convince somebody because, they said it prettily or something. We're looking to show people what's right. Okay. So if you go look up a proof online and present it in class, you got nothing out of that. You just threw away an opportunity. So the honor code here is a really big deal. Represent your work as your work. Okay. If you don't, I'll know. There's not a great way to back that up. There's not a specific way I'll know. I'll just know. There's a certain thing about kind of your intellectual fingerprint that if you keep representing work to us that you could not have done yourself, it'll become obvious. Okay. So I'm just going to ask you all, be cool, represent your work as your work. You're going to do fine. Don't freak out about grades. Okay. But plagiarism, it's not just don't copy word for word. It's don't steal other people's ideas. Okay. So in any case, we will, in large part during the class, be doing something that's kind of collaborative. We will discuss things, we will talk about things. Those are all totally fine. But you do need to kind of produce on your own. And then what you produce, you talk about and figure out stuff. Okay. This bit here about the unauthorized use of materials, I'm sure that if you know how to look for them, the solutions to every problem that we'll do during this class have been posted online somewhere, but don't. Okay. All right. Attendance policy. Try not to miss too often. If you have to miss, let me know that you have to miss, and that's an excused absence, and it's no big deal. Okay. But if you miss and have to let me know after the fact, I do ask you to, give me some sort of legitimate excuse, okay, of what was going on. So note here this bit about missing more than 6 class meetings is cause for being dropped from the course. I don't foresee that happening very often, but if you should miss more than 6 times, so that would be the 7th time, then I would look into that option. So our grading system, we will grade on a really boring system here of 90, 80, 70, 60. Oh, no, that's not what I set up. I set it up to go down to 55 for the D minus and stuff. Yeah, okay. I don't think this is anything that y'all need to worry about. The real worry for y'all is going to be, are you getting an A minus, an A, or an A plus? I've looked at the course roster and I know who's in the class. That's the only thing that you have to worry about is where in the A range you end up. The major graded assignments. Let me just say something that participation is basically just showing up and not being asleep. Okay. It's 10% of your grade. It doesn't count for that much of a thing, but it's something where it's easy to get a few points. Okay. Regular presentation is going to be the main thing of the course. And I'll say more about that in a minute, but that is the bulk of the points. You're going to come to class every day. You should have something to put on the board that you have either solved something or you've tried to solve something and you want to talk with other people about what you've tried. Okay. Don't make those lame. Okay. Make it be legitimate stuff that you want to talk about. I have in the past had people for this sort of thing give presentations where they just rewrote the problem assignment and they said, I don't know, and tried to elicit conversation. And I was like, we'll say more about what we're expecting on that in a minute. The written summaries is going to be that once a week, I'm going to ask you to write up really nicely one of the problems that's been discussed in class. You will get to choose which one, okay? But I want you to write up something that it was not your presentation, okay? This means that you have to pay close attention to what the other people presented. Okay. Final bit here is the final presentation. So you're going to be presenting all semester long. During final exam week, you'll come in and you'll present something then. It should, in theory, be something that's a little more than what you presented during the other parts of the semester. Okay. Try to find something that's really good to present then. That's going to be the main thing. And of course, I have an alarm on that I did not know I had on. Hopefully it will not say anything more. Okay, anyway, the final presentation.
Hey, Ben, go get Arthur. Have a nice day.
Literally turned the volume off and it just turned it back on. Fine. Okay, final presentation, yeah. So assignment details here. So regular presentation stuff. Okay. And I just noticed a typo. So we meet 2 times a week. So all right. So yeah. With regard to this regular presentation stuff, we present stuff all the time. That's what we're going to do. Notice that I did not list in the grade stuff anything about exams. In a sense, every day is an exam. That's terrifying, right? But yeah, what we will do a lot of is working out things. And I want you all to get very used to just explaining things to people. And that bit of explaining things is a big skill to have kind of in life, I guess. But it's going to figure into other things that you might do that are outside of math. You're going to explain things logically, and that means you have practice at being right about things, or more to the point, not being wrong. Okay. So these regular presentations, the way this will run is that every day I will come into class, check the attendance. There's not many people here, so it'll be real quick. But I'll check the attendance and I'll say, hey, does anybody have anything they'd like to present? And that's your option or your opportunity to hop in and just do things in whatever order. Okay. But I want to get everybody to volunteer for something first. And then anybody who hasn't volunteered something, I'll try to coerce into to presenting something. And then we'll kind of go back around and I'll try to get folks to do stuff again. Okay. If you don't volunteer, then I will go down through the list and ask each person, what have you been working on, and that sort of thing. So with regard to these presentations, yeah, it's just what you're doing every day. Yeah. These presentations are not going to be the technology-based presentations, slide shows and stuff like that you're used to from other classes. This is going to be, here's your chalk, go up to the board, write down the problem statement and write down your reasoning and talk to us about what you've got there for a solution. Okay. At first, you will very much need to write down a solution and turn around and talk to us. But as you do this more and more, I want you to learn the skill of writing down a sentence or two and then coming and talking to people about why that makes sense and stuff. And so really, we've got this thing where everybody in the Guilford classes they're supposed to be trying to learn how to do presentations. Yeah, every day. That's what we do. Okay. This is what this is probably one of the 2 or 3 hardest skills that you have to learn as a student and as somebody in academia in general, is how to convince other people that you're right from, talking to them and stuff. And while you're at the board, the other people sitting down are having to learn how to critique what you're doing. Okay. So in a sense, the participation portion of the grade, I guess, maybe I should be making that more and then recording whether or not you're appropriately critiquing people, but that's hard to do. Okay. So anyway, you're going to present your solutions to stuff. As we go along, you'll get better at doing it. Okay. Yeah. And I said something about the written summaries and stuff. Okay. Yeah. That's what I want to talk to you about on that. Now I want to do a little bit of a presentation here. And it is technology enhanced and stuff, just because it's easier to do this with something that's prepared ahead of time instead of just you're getting it from my talking. or am I trying to write it down as we go here? So welcome to actual math. You've taken calculus. Some of y'all have taken some of the other math classes outside of the calculus sequence as well. And so you have some idea of how to use math to calculate things that has to do with numbers in general. But this is what it's really all about. The mathematics that people practiced in ancient Greece didn't have numbers in it. The Greek numbering system is weird. Okay, they used letters for numbers, and so which led to numerology and all kinds of weird things. But when somebody says in a modern geometry class, a squared plus b squared equals c squared, we all know what's going on. But that would have been bizarre to them because alpha is the number 1, beta is the number 2, c, I guess gamma is the number 3. 1 squared plus 2 squared is not equal to 3 squared. So what the hell are you talking about, dude? They didn't have a concept of algebra or having letters stand for numbers the way that we do. They would instead have said the square produced upon the hypotenuse of a right triangle has an area which is equal to the sum of the areas of the squares produced upon the other two sides. Yeah. So they did a lot of really abstract reasoning of coming to conclusions like that. There are other area things that they came to, and things they're much more abstract too. We're going to be looking at different kinds of stuff, but we're going to be applying that sort of thing. And so I like to, did I hit the right button there? Hang on. That if I hit slideshow first on that, and then I hit share screen. Okay, looks like it doesn't matter which one I do. Okay, I'll do that one. So this is this is kind of a schematic that gives you a notion of how to math, really how to reason. So over here, notice that we have this idea of observations. When you're reasoning about things, you look at stuff in the world and you make observations. Hey, look, the squares on the sides of this right triangle happen to have areas that add up in a certain pattern. So observational sort of observational sort of things is where reasoning starts. But then after you've observed something, you should ask, why would that be true? And that's not trivial at all. You have to kind of hunt out structurally, what is it that's going on that might make that actually be true? And if you figure out the reason why, then you construct what in math we refer to as proof. In other disciplines, you don't present proof, you present evidence. And I like to say that's because we're cooler than the other disciplines. We get actual proof, which means we absolutely positively can't be wrong, as opposed to we have lots of strong evidence and people have repeated our experiment and had the same things show up and so forth. We've got something that has to be true. Although occasionally people then find holes in the proofs after we've presented them. But once you have a proof that something is true, you should be going back to the proof and trying to figure out exactly what was going on in it. If that proof that you've got has stuff in it that's unnecessary, strip it down, make it a better proof by putting less stuff in it. You are not doing this by examples. You're trying to figure out why and strip it down to just exactly why. Sometimes, if you're not using all of your assumptions, sometimes you've got a better proof than what you started with your observation. And sometimes that will let you recycle and make new observations, because you can take the principles that caused your initial observation to work out, combine them in different ways, and you might have a new observation. Or you might find out that you didn't need all of the stuff that you started with. So anyway, this is kind of the reasoning cycle. In a sense here, the reasoning and the re-examining are kind of the same thing happening over and over again. It's just depends on how you use them. If you use them to recombine in a different way in order to make different observations, then the examinations is somewhat different. So, all right. So let's talk a little bit about what you have to do in math, what kinds of things are going to crop up. And the big thing is that we will define stuff. But you've got to understand that it's not possible to define everything. Have you ever dealt with a 3-year-old who's just learned about the notion of asking why? You explain something to them and they'll say, why? Maybe you start with, why is the sky blue? And you try to explain something about photons and reflecting and refracting and so forth. And they say, why? And you're like, why do photons refract? Well, because they're hitting these other ions and blah, blah, blah. And they'll say, why? If you keep going with that, eventually you get just to a point where you can't ask more, you know. I was once sitting on the steps of sitting on the steps of King Hall, and there was a science fiction convention going on, and somebody had brought a whip, and they were cracking a whip. And the person standing next to me said something about, leather breaking the sound barrier. And I said, I was thinking about that, and I don't think that's how that works. And he said, well, of course it is. And I said, well, why does it work like that? And he started to explain things to me, and every time he would say, well, you know this, I'd say, yeah, I don't think I do. And after about half an hour, he finally said to me, at what point do you reveal to me that you're a particle physicist and knew how this all worked in the first place? And I said, well, I won't, because I'm not a particle physicist, I'm a mathematician. And he laughed, and we dropped the conversation. But things always have to start somewhere. You can't just keep going forever with how do you define this, how do you define that. You've got to have some things that you assume. And we'll talk about those. We'll talk about those a little bit as just some collected conceits that we don't define. But for those things that we do define, they all kind of boil down to this. An object 1 is an object 2, provided it has property 1. So you'll start out with an object. Maybe it's a number. Maybe it's a point in space. Maybe it's a topological donut, but you have to have some idea of an object. And then you're going to say it's a particular kind of object provided, and then you have some property. An even number is a number which is a multiple of 2. Don't say it's divisible by 2. Say it's a multiple of 2, because that makes it easier to deal with. A prime number is a positive integer greater than 1 which has no factors other than one and itself, integer factors. So, but your definitions, they always have to start out with, it's a kind of thing. It's a positive integer. It's an integer. It's a number, something like that. And then you'll define a particular kind of them with some property. Okay. So you can think of those as saying, if object 2 obeys property 1, then, if object 1 obeys property 1, then it is object 2. If if an integer is a multiple of 2, then it is even. Okay, just rephrasing it in a different way. Axioms and theorems are different things. Axioms are things you assume because there's no way to prove them. And theorems are things that are true that you prove using the axioms. Okay. But axioms and theorems will both have a statement that boils down to something like this. If object, whatever the object is, has property 1, then the object has property 2. What are property 1 and property 2? They could be anything, right? But we have that sort of structure on things, that you have an axiom, and it's telling you that having one property will give you another property. So that's we'll have them be slightly more concrete when we actually do problems. But you may see this notation down here below. Can I? Nope, it will not let me highlight it. Oh, well. So A arrow B is sometimes read as if A, then B. Okay. So the A is some statement, and then the B is some other statement. And when you state an axiom, you are saying that this if-then statement is true. Okay. That anytime that the if part is true, the then part has to be true as well. Okay, so I've had friends who are in philosophy who think it's hilarious to point out that this is all math is, modus ponens, over and over again. And modus ponens boils down to that you have one statement that you are assuming is true. I don't remember what that one's called. There's names for each of these pieces here. And I've forgotten what you refer to the 3 pieces as. But you say, if condition 1 is true, then condition 2 is true. I didn't put is true on there, but yeah. And then you say, then you have some way or another of knowing condition 1 is true. And that tells you that condition 2 is true. That's all we do. We read a theorem that says, if A, then B, and then we somehow have identified that A is true, and we'll conclude that B is true. We do it in kind of a complicated fashion. But shorthand that you may see on this is if A, then B, and A. You may see a little caret used for that. Say something about later. And therefore, the 3 dots means therefore B. So you can draw a conclusion there. So the typical example in a philosophy class is you say all men is mortal. Oh my God, I can't. Oh, I'm sorry. I can't let that pass. All men are mortal. Okay, back to it. So all men are mortal. Socrates is a man. Therefore, Socrates is mortal. So you're just drawing a conclusion. It's probably in kind of an obvious way. But that is what we do. Now, we have another method of reasoning called modus tollens that is dependent on the same thing, but it's a little bit more indirect. So you start out with the same thing about if condition 1 is true, then condition 2 is true. But then you say condition 2 is false. Well, if condition 1 were true, condition 2 would have to be true. So since condition 2 is not true, it's false, then condition 1 has to be false. Okay, so you'd say if A, then B, and not B, therefore not A. Okay, if you're saying, oh, that seems pretty obvious, great. If you're saying, I'm not, here's the example. All men are mortal. We had that before. But Zeus is immortal. Therefore, Zeus is not a man. Okay. So notice on this, the all men are mortal. If X is a man, then X is mortal. Zeus, the X, is not immortal, therefore. Okay. So all right. Then if you're good with that, we're going to talk a little bit about some of the logical connectors. And these are things that we'll get used to, but they are a little odd at first. Okay. If you have taken a discrete math class, you will have seen this done in a slightly different way than what we generally do it. And so I thought I would try to refer to that as we go along here. So if you got two statements of fact, maybe these statements are X is in set A, X is in set B. We often make one of these Venn diagrams to help us see what is going on with this kind of thing. So the stuff that is in set A, oh, come on, I did not click that. The stuff that is in set B, okay, when we say something about and, X is in set A and X is in set B. The and means it has to be in both A and B. Okay. So if you've got a statement like that, it can be either true or false, then we sometimes think about this thing of a truth table. And if you're okay with using trues and falses for it, great. If you'd like to use zeros and ones because you want to connect it more to computer science and programming sorts of stuff, that works too. Okay. But an and statement, you can only get things that are part true for an and statement if both of the other conditions were true. So that means if you've got two statements, A and B, and both of them are true, then the statement that says A and B is true. But if one of them is false, then the A and B is false. So either way that you go there. And of course, if both of them are false, then clearly you get a false statement out of that. So if you want to talk about this in picture sense, the stuff where we talk about X is in A and X is in B, the stuff that's in both is X is in A and X is in B. If you talk about X is in A, but X is not in B, you get this stuff over on the left. If you say something about X is not in A, but X is in B, you get this stuff that's over here on the right. If you say X is not in A, and also X is not in B, then you get stuff that's outside of both circles. Okay. So this color scheme of doing things with the Venn diagram often helps people just kind of spot what's going on here. Then if we talk about an or statement, then that is the stuff that has either one of the conditions being true. Okay. And so we say something about A or B. And so we get the stuff that's in A but not B, the stuff that's in both A and B, and the stuff that's in B but not A. And so if we kind of keep these pictures in mind of what we're doing here and equate being in a set with satisfying some condition, in this case, the condition was being in the set. That wasn't very interesting, but as we go along, we'll have other actual conditions to think about. So, but if you think about that sort of thing visually, sometimes you can reason things out a little bit easier than you could have otherwise. Okay. And then this last part here is not just meant to be a cool picture of the moon, haha, but rather the idea of having true statements, having if A, then B be true. And in those cases, we would have we would have a statement like X is in, if X, yeah, we'd have the statements X is in A and X is in B. And we would say, if X is in A, then X is in B. When is that true? Well, this stuff over here that's in A but not B does not make it true. But this stuff which is in both, if X is in A, then X is in B, okay, then those are true as well, or those are true. The ones that may be surprising are the B and then the outside of these things. The stuff that's over here in the B has when you say something about if X is in A, then X is in B, well, X isn't in A. So it doesn't tell you anything about whether it can be in B or not. And so this setup here of having things be vacuously true by not satisfying the if statement is kind of a weird part of having statements be true when it's not really relevant that you can use them. So, all right, I'm going to go ahead and stop there. Okay. This is a lot of what our reasoning is going to be about. I am going to have at class time some pages for y'all of problems to work on, and you're going to work on trying to prove things. And we'll get back together and we'll look at how you're doing with those. But that's what we're doing. Okay. If you got any questions, feel free to contact me, email, call me, whatever makes sense, whatever works for you. All right. And I will see you around 11:30 on Tuesday. Thanks.